Force Method, Part 2. This is a continuation of Lecture SA 24, where we began discussing the use of the force method for analyzing statically indeterminate structures. Please watch that video for an overview of the method and how it can be used to analyze beams having a degree of indeterminacy of 1. In this lecture, we are going to focus on the use of the method for analyzing beams with a degree of indeterminacy of 2. Here is one such beam. It rests on 1 pin and 3 rollers. Hence, there are 5 support reaction forces. Although the beam is going to deform under the applied load, like this, but there is no vertical displacement at the supports. Vertical displacement at A, B, C, and D remains 0. Since the degree of indeterminacy of the beam is 2, if we remove 2 of the vertical reactions, we get a statically determinate beam. Let's pick By and Cy as the redundant forces. If we remove them from the free body diagram, we get. Consequently, since points B and C are no longer restrained against vertical movement, the beam is going to deflect downward like this. Let's refer to the vertical displacement at B as delta B, and call the displacement at C delta C. Okay, now visualize a pair of upward forces, one placed at B and the other placed at C, that collectively push the displaced beam up such that the vertical displacement at B and C reverts back to 0, like this. These forces, labeled By and Cy, represent the support reaction at B and C, respectively. In order to come up with the correct equations for calculating By and Cy, we need to examine them individually. First, let's consider the effect of By on the beam. If we place an upward unit load at B, the simply supported beam, without the applied distributed load, is going to deform like this. Note that there is a vertical displacement at B, and there is one at C. Let's refer to the displacement at B as delta BB, and to note the displacement at C as delta CB. Why am I using a double subscript notation for these displacements? Because I want the symbol to denote the location of the displacement, as well as of the location of the unit load causing the displacement. So this refers to the displacement at B due to a unit load applied at B, and this refers to the displacement at C due to a unit load applied at B. The first subscript points to the location of the displacement. The second subscript indicates the location of the unit load that has caused the displacement. Now, if we replace the unit load with By, these displacements can be written as By delta BB and By delta CB. Next, we want to consider the effect of Cy on the beam. If we place an upward unit load at C, the beam is going to deform like this. We refer to this displacement as delta BC, and we call this one delta CC. Delta BC is displacement at B due to the unit load placed at C, and delta CC is displacement at C due to the unit load at C. Now, if we replace the unit load with Cy, the displacements can be written as Cy delta BC and Cy delta CC. Let's summarize what we have so far. The simply supported beam subjected to the uniformly distributed load has downward displacements, delta B at B and delta C at C. The simply supported beam subjected to the upward reaction force By has displacements By delta BB at B and By delta CB at C. And the simply supported beam subjected to the upward force Cy has displacements Cy delta BC at B and Cy delta CC at C. We also know that the sum of these 3 diagrams gives us this diagram, meaning delta B equals By delta BB plus Cy delta BC. This equation is a mathematical way of stating that total displacement at B must be 0. And delta C equals By delta CB plus Cy delta CC, which means the beam's displacement at C must be 0. So we end up with a system of linear equations. We have two equations and two unknowns. By and Cy are the unknowns. And these displacements are coefficients, which we can calculate using, say, the virtual work method. We call these compatibility equations. The solution to the compatibility equations gives us two of the unknown reaction forces. We can then use the static equilibrium equations to determine the remaining support reactions. Let's illustrate the entire process using an example. Suppose we have a beam subjected to a uniformly distributed load of 50 newtons per meter. Assuming a constant, EI, we wish to analyze the beam using the force method. We start by drawing the structure's free body diagram. Since the beam's degree of indeterminacy is 2, we need to pick two of the unknown reactions as redundant forces. Any pair of vertical forces will do, as long as the remaining structure is stable. Let's pick By and Cy. Now remove them from the beam. Here is the resulting simply supported beam. The beam is going to deform like this. Note the vertical displacement at B and at C. I can now write the compatibility equations. This equation states that, at point B, the upward displacement due to the redundant forces must be equal to the downward displacement due to the applied load. This equation makes the same statement, but about point C. Upward displacement due to the redundant forces must be equal to the downward displacement due to the applied load. There are 6 displacements here. Can you identify them on these diagrams? Pause the video if you want to give it a try. This is delta B. This is delta BB, displacement at B due to a unit load applied at B. This is delta BC, displacement at B due to a unit load applied at C. This is delta C. This is delta CB, displacement at C due to a unit load applied at B. And this is delta CC, displacement at C due to a unit load applied at C. By the way, calculating these displacements is the most time-consuming part of the force method. I am going to use the virtual work method for this. But since the method was explained in previous lectures, I'm going to go through the calculations rather quickly without any commentary. If you're not sure how the virtual work method works, please see lecture SA22. First, let's calculate delta B. So delta B equals, now let's compute delta C. Delta C equals, next we calculate delta BB. And here is delta BC. Finally, we determine delta CC. And delta CB. Okay, now we're ready to solve the compatibility equations. Here are the two equations in simplified form. Solving them simultaneously, we get By equals and Cy equals. Now we are ready to calculate the remaining support reactions using the static equilibrium equations. Here is the result of the analysis. We will continue our discussion on this topic in the next lecture. Here are a few exercise problems involving statically indeterminate beams and frames, all having a degree of indeterminacy of 2.